Okay, so let us begin. So, we basically, so let me do a quick very quick recap of where we were. We are basically looking at soft decision decoding. Okay. The setting is BPSK over AWGN. Okay, so this is a kind of a technical way of describing the setting BPSK over AWGN, and we want to do soft decision decoding. Okay, so the first kind of decoder that we are looking at is the ML decoder, okay, which tries to compute f of r given code word equals u, maximize over all u in the code and take the argument as your C hat. Okay, and this f is basically stands for PDF. Okay, you can think of probability if you like, but this is the expression. Okay, so let us try and simplify this. Okay, so this f of r given C equals u. Okay, so all this is quite standard, but I am doing it a little bit more slowly so that we can see what is happening. This is going to be f of r given s equals 1 minus 2u, right. So, this guy, okay, so what is this? So, this is a little bit more maybe it is a little bit more confusing. So, I will do this in a little bit more detail. Okay. This one is f of r1, r2, so on till rn given, let us say some s1, s2, so on till sn. Okay. So, you can write, so remember s1 through sn is given. Okay. So, it is some known symbol vector. Once the symbol vector is given, the received values become conditionally independent. Okay. So, you can write, if you want to write this conditional PDF, it is the same as the product of f of ri given si I equals 1 to n. Okay. So, if I do not have the conditioning, I cannot write the joint PDF of r1 through rn as the product of the PDFs of ri, that is definitely not possible. Once I have conditioned it, then the s's have become fixed. So, given that s is fixed, the conditional PDF becomes product of the individual PDFs. There is more than one way to see this, hopefully it is clear to you. Okay, if not, try and convince yourself that this is true. Okay. So, once you have that, this is an easy expression to write down. What is f of ri given si? 1 by root 2 pi sigma e power minus ri minus si squared divided by 2 sigma squared. Is that okay? Si is something fixed. Okay. So, when I multiply, so hopefully this is clear. Okay. So, one general thing I should warn you about these courses, I mean if you do an error control coding course today, we started with linear algebra, linear block codes, okay, and then we moved on to abstract algebra, finite fields, algebraic codes, and then now we are moving on to probability. Okay. So, probability will play a big role for the rest of the course. Okay. So, you need multiple fields and you have to be a little bit comfortable. It is not that we are going deep into any one area, but still you need to be a little bit comfortable with how these things interact with each other. Okay. So, let us see. So, now if I do the multiplication, I am going to get, remember what am I computing, f of r given c equals u, or let us say s equals, or let us say c equals u. Okay. This is the product of, okay, I wrote it down as a product. So, when I multiply it out, I will get 1 over root 2 pi sigma occurring n times, and then I have e power minus 1 by 2 sigma square sum from I equals 1 to I ri minus si squared. Okay. So, right, I am multiplying the e power minus something. So, in the exponent it will add, I will get this expression. Okay. So, this is exactly same as before. Okay. So, now remember what is S, the only conversion I should remember here is S is 1 minus 2u. Okay, so that is the conversion I should remember that. Okay. So now I am trying to maximize the left hand side, okay. That is the same as maximizing the right hand side obviously, okay. But now that is the same as minimizing the exponent, right, it is e power minus something. So if you want to maximize the whole thing, it is the same as minimizing the exponent, okay. So maximizing f of r given c equals u over u is the same as minimizing summation of this guy you can write it in compact as r minus s squared, okay. So this is the Euclidean distance between the vector r and the vector s, okay. So minimizing r minus s squared over u and s being 1 minus 2u, okay. What is u? U is in the code, okay, so I should write that down. Okay. All right. So, this is the Euclidean distance between the vector r and the vector s. So, you have to imagine that these two guys are in the real vector space with n dimensions, okay. Is it okay? So, once again you have a very nice geometric picture, okay. So, what is this geometric picture, which is very similar to before. If you have 0 1 n, no, it is not 0 1 n now, okay. So, that is the difference. My circle now is R n, and then I have stars. What are the stars? Symbol vectors, okay. So, code word symbols, so to speak, okay. So, you convert the code word into symbols. So, these are the S's, okay. So, these guys are the stars are the 1 minus 2u when u is u belongs to the code, okay. So, these are, you can call them various ways, I mean symbols, symbol vectors corresponding to the code word or coded symbols, something like that, code symbols or something like that, okay. So, what is transmitted is one of these stars, okay, one of these things is transmitted, and what gets added to it is some random vector z which will take it away to any one of these points, okay. So, all of these points, in fact, there is an uncountably infinite number of these things. I am just drawing a few dots, don't be under the impression that those are the only possibilities, okay. So, you have a huge number of possibilities, but they will be around the stars, right. So, they will be around the stars, okay. Suppose I am here, that is my received value r, okay. What should my best possible decoder do, the maximum likelihood decoder? You should look at the distance from the stars, okay, all of them, you have to look at all of them, well, all of them, and then pick that one which has the smallest possible distance. So, the ML decoder is finding closest code word symbol, okay. The closest now is defined with respect to Euclidean distance, okay. So, it is nice to have this view, I mean you have to view, this is in fact it is very reminiscent of the binary symmetric channel view, right. You remember when we were doing hard decisions, not even thinking of Rn, just 0 1 n, once again we had stars which were the code words themselves, and then errors got added to it, and then the ML decoder simply looks at closest code word in what sense, in Hamming distance, okay. So, now you have come to Rn, and once again you have an ML decoder, but the distance now is not Hamming, but it is the Euclidean distance, the regular distance that you have in the n dimensions, okay. So, in fact, I mean I have been talking about BPSK a lot here, but BPSK played very little role in this entire derivation. If you see for any other constellation that you might have also, a similar rule will come, okay, finally. If you list all your symbols that are possible, clearly the best possible symbol vector is the closest one in Euclidean distance. There is nothing wrong with that. Okay, so BPSK is just playing a very small role here. Okay, hopefully that is clear to you. Is that all right? Okay. So for BPSK, you can do a further simplification. Okay, so far BPSK did not play a big role, like I said. If you assume BPSK, okay, so let us look at this summation I equals 1 to n Ri minus Si squared. Okay, this is summation I equals 1 to n Ri squared minus 2 Si Ri plus Si squared. So far I have still not used any BPSK knowledge. Okay. So now I am trying to maximize over all possible vectors S. Okay. So the first term here is not going to be affected by changing S. Okay. So this I can drop from my calculation. Now what about Si squared? This is always equal to 1 for BPSK. Okay. Again, if I change the symbol vector S, because it is BPSK and I pick this minus 1, it is always going to be a constant. Okay, it is 1. So I do not have to bother with that term also. Okay. So if I want to minimize this expression, over u in code S 1 minus 2 u. Okay, this is important, BPSK is very important. This is the same as maximizing over the u in code S is 1 minus 2 u what Si Ri, summation I equals 1 to n Si Ri. By what do we know this expression more familiarly? This is the dot product between R and S, or the correlation between the two vectors R and S. Okay. So of course this used BPSK. Okay. If you did not have BPSK, this will not be true. You have to subtract this Si squared from the correlation. Okay. So you have to normalize the energies in the correlation. Once you do that, this is still useful, but this is also a standard notion in communications and detection, that you can do correlation. Okay. So the way you think of dot product is, you start look from the origin, you have a received vector R, you project it onto every symbol vector, okay, whichever gives you the largest projection, you pick that one. That is the same as minimizing the distance, we know that from classic results. Okay. So that is the same idea here. Is that okay? Okay. So now it is time for an example. Let us do a very simple example and see how this works. The example we will do will be a 3-1 repetition code. Okay. So 3-1 repetition code, I am going to give you some received vectors, okay, and you have to tell me the message. Is that okay? 3-1 repetition code, BPSK over AWGN, of course it is always going to be true. Okay. The way we will do this example is, I will give you some received vectors, you have to do, let us say, ML soft decoding and tell me what the transmitted bit was, I mean the message bit, you can directly find the message bit or the code word, any one you can do. Is that okay? So the first one I am going to give you is let us say 0.1, 0.2, 0.3. Everybody is very quick to point out. Okay. So yeah, I mean, so you can do the correlation or anything else, but remember you have to only correlate with two different symbol vectors. One symbol vector is +1 +1 +1, the other symbol vector is -1 -1 -1, +1 +1 +1 corresponds to 0, -1 -1 -1 corresponds to 1. Okay. So if you do the first correlation, R dot 111 simply gives you 0.6, and r dot minus 1 minus 1 minus 1 is clearly going to give you something negative, which is in fact minus 0.6. So, clearly positive number is greater than the negative number. So, we pick this. Okay. So, let us try and write down a general expression. Suppose I say, suppose I do not really give you the r, say r1, r2, r3. Okay. What are you going to do? You are going to do a dot product with 111 and compare it with the dot product with minus 1 minus 1 minus 1. So, what is the condition that m is 0? M is 0 if r1 plus r2 plus r3 is greater than minus r1 minus r2 minus r3. Now, you can bring this to this side and you will get 2 times r1 plus r2 plus r3, and 2 is clearly positive. So, you can throw it out. So, this becomes equivalent to simply r1 plus r2 plus r3 greater than 0. Okay.
This
okay. So, when will, okay, hopefully this clear, is okay, no? Okay. So, this is when m is 0. When will you say m is 1? r1 plus r2 plus r3 is less than 0. Okay. So, that is all. It is very easy to look at these two conditions. So, any other r1, r2, r3 I give you, you can very quickly find out. Okay. Next thing I am going to ask you is a little bit more devious. Okay. So, what I want you to do is, I want you to come up with an r, okay, okay, which will give me different answers under optimal hard decision decoding and optimal soft ML decoding. So, optimal hard ML decoding and optimal soft ML decoding. Same R, did you understand the question? Hopefully, the question was clear. So, it is an interesting question to consider. Okay, I want to come up with an R which, when I decode with hard ML, basically I make a hard decision and then I run my syndrome decoder. Syndrome decoder is very easy for the repetition code, right? It's just majority, you see which one is larger. I should get, let us say, m equals 0, and then if I run the same thing with soft ML, I should get m equals 1. Put something big, right? So, if you make it 0.1, 0.1,
minus
0.3,
anything greater than minus 0.2. So, you make it minus 1. Okay. So, what happens now when you take hard decision is, you are treating a value 0.1 the same as a value 1, okay, 10 times larger, but you are not distinguishing between the two, you are simply slicing one as 0, slicing the other as 1. So, when you do hard decision, you are going to get 0, 0, 1, and that when you do a syndrome decoding will go to 0, 0, 0, message 0. Okay. On the other hand, when you do a soft decoder, you are taking into account all these things. So, you are looking at R1 plus R2 plus R3, which clearly goes to minus 0.8, and that will give you m equals 1. Okay. So, that is soft ML. Is that okay? So, this is a simple way in which the 3-1 repetition code works. Any questions on this? Okay, so this is the simplest possible code, so it is very easy. Okay. So, you can also generalize. Suppose I have an N1 repetition code. Okay, and I do same BPSK over AWGN. What will be the decoding rule? M will be 0 if, yeah, so summation over Ri, I equals 1 to n is greater than 0. Okay. So, you have a very simple ML decoding rule for repetition codes. Okay. So, you add up I equals 1 to n Ri, if it is greater than 0, you say message was 0, if it is less than 0, you say message was 1. Is that okay? Is there a question? Something is disturbing you?
Twice if we have substantially high noise samples, even that is allowed, but one high value is not allowed. It's like,
what do you mean by not allowed?
it's like something like,
that's the only question I have. Okay, so the observation is making us, it seems like hard ML and soft ML agree when there are two noise values which are large, but if there is one noise value which is large, then they may not agree. Is that what you are saying? Yeah, I mean, that is correct. That is what will happen. So the question of when the hard ML decoder and soft ML decoder will agree and all are, at least I do not know, a very simple description, it is a bit complicated. Okay, so it is very hard to answer these things. So you have to, so that is the modern view of things, right? You do not have any deterministic clean answers. I mean, it is just, it works the way it works, very hard to analyze this. Okay, but for repetition code things are much simpler. I mean, we will see as we go along. Repetition is very easy, the other ones are tough. Even the simplest possible code after this we will see will be much more difficult. You can't get a handle on what is happening. Okay. So this is the thing, m is equal to 0. So now what I want you to do, which is a little bit more challenging, is try and find out probability of error for the soft ML decoder. Okay. So it is a little bit more twisted, so I will lead you a little bit, I will not just leave you blank like this. Okay. So let us say m equals 0 was transmitted. Okay, what is the probability that you will decide that m equal to 1? Let us compute that. So let us try to find probability that summation I equals 1 to n Ri is greater than 0 given 1 1 1, right. This is the probability that you will make an error if less than 0, right, sorry, less than 0, sorry. But remember, conditional on the fact that I sent 1 1 1. Okay. So if you sent 1 1 1, what does summation Ri become? So if you sent 1 1 1, summation Ri is simply normal with mean 3 and variance 3 sigma squared. Is that okay? So it is basically 1 plus sigma square, 1 plus z1, 1 plus z2, 1 plus z3. So you will get 3 plus z1 plus z2 plus z3. Zi is basically IID normal 0 sigma squared. You add 3 of them, you get normal 0 mean 3 sigma squared, and 3 is 3 plus that simply gives you normal with mean 3 and variance 3 sigma squared. Is that okay? Fine. So when will a normally distributed random variable with mean 3 and variance 3 sigma square be less than 0? You can do that with q. This is simply q of 3 by root 3 sigma, which is q of root 3 by sigma. Okay, so I have done it for n equal to 3. Okay, so this is for n equal to 3. So now there is no reason why you can't generalize it to an arbitrary n. Okay, so if you put n here, this will become normal with n and n sigma square. This will become n by root n sigma. So essentially you will get q of root n by sigma for the general case also. Okay, so it is a very quick argument for the probability of error. You also have to argue for the opposite case, m equals 1, but it will be symmetric. Okay, so you do not have to worry about it. The channel is a very nice channel, so you will get symmetric. So you can fix at m equals 0 and you can do the problem. Is that okay? So you get q of root n by sigma. Okay. So I want to point out something very interesting here. So if you use the n comma 1 repetition code, probability of error under ML decoding, which is easy to do. Okay, right? Probability of error soft ML decoding for repetition code is very easy. All you need is an adder, you can implement it. Okay, this goes as q of root n by sigma. Okay, so what is the uncoded probability of error? If you do not code, all this is for BPSK over AWGN, right? So remember that all this is for BPSK AWGN. If I do not do any coding at all, probability of error is q of 1 by sigma. Right? So this is standard BPSK, simply q of 1 by sigma. Is that okay? Which will be lower? 210 by sigma, Q of 210 by sigma will definitely be lower. So, it looks like repetition coding is buying you a big advantage, okay, but there is one minor cheating here. What is the cheating that I am doing? Yeah, so you are sending n symbols to send only one information bit, okay. So, the amount of power you are spending to send one information bit in the coded case is n times as large as the power you are spending in the uncoded case. In the uncoded case, every symbol carries one information bit, okay. So, you are spending n times as much power and you are not accounting for it in your SNR computation, okay. So, remember for the uncoded case, the SNR or SNR per information bit, what is SNR by the way? Signal to noise ratio. No, I did not say it out loud, hopefully it is known to most people here. This would be 1 by sigma squared, okay. So, the symbol power is just 1, right. So, either minus 1 or plus 1, the variance is just 1. What is the SNR per information bit here? Okay, so, SNR per information bit is also called EB over N naught for instance, okay. So, the SNR per information bit for the repetition code is what? N by sigma square, okay. So, this is EB over N naught. It turns out if you express probability of error in terms of EB over N naught, you will get the same answer for both, okay, right. Instead of expressing in terms of sigma, if you express it in terms of EB over N naught, you get simply Q of square root of EB over N naught. So, if you are constrained by SNR per information bit, which is what you will be constrained by in most cases, repetition code does not buy you any advantage in probability of error. For the same SNR per information bit, you get the same probability of error whether or not you do repetition coding, okay. If that is a constraint, then there is no problem, but if energy per bit does not matter, what matters is only energy per symbol, then you will get a big benefit by repetition code, okay. So, that is something to remember, okay. If only 1 by sigma matters, then you get a big advantage, but if amount of power you spend per information bit matters, then you do not get any advantage. Is that okay? So, this is something that you have to account for usually when you do coding, and I will talk more about this in a general case later on, but it is good to know this even for the repetition code, okay. So, the way in which you phrase it is to say that repetition code does not give you any coding gain in EB over N naught, okay. You do not get any coding gain, so to speak. Come back and see these things in more detail later, but for now this is a nice thing to look at. Okay, so let us do one more example just to get a little bit more confused, okay. Simple enough example. Let us say my code now is a 4-2 code, illusion.
Yeah, it's not getting anything in terms of the probability of error. So, what is this question of maximum distance separable?
Yeah, well, it's more of a, so okay. The question was, does maximum distance separable mean a lot of coding gain? That is your ultimate question. Okay. Well, obviously it does not, right? So, as we have shown, so MDS by itself does not mean much. So, the rate matters. Of course, minimum distance matters in coding gain also. Can't say no. Okay. Ultimately, it will play a role. Particularly at very low error probabilities, it will play a big role, but you will see there are lots of other things other than minimum distance also, okay. Okay, so this is a 4,2 code, okay. So, if you do BPSK AWGN and if I give you an R, which is some R1, R2, R3, R4, okay, it's immediately a little bit more complicated. It's not as easy as the repetition code, right. So, I have to decide between 4 different situations, message being 0 0, 0 1, 1 0 and 1 1. Let us say the first 2 are the systematic locations, okay. So, you have to decide between the 4 possibilities and you have to do all the correlations, right. So, you have to do 4 different correlations. Okay. So, there might be smart ways to minimize your computation. Okay. So, there are lots of additions that you might repeatedly do. Okay. For instance, I mean you can see some patterns here. There are smart ways to reduce your computation, but essentially you have to do those correlations and you can't avoid it. Okay. And it is very hard to compute, for instance, probability of error. Okay. So, let us try and do this, let us try and write it down in general and see what happens. Suppose I write down R being R1, R2, R3, R4. Okay. When will I say my message was 0 0? I mean talking about, okay. The question is, can we do something very smart for this specific case, right? So, let me write it down, then we will see. Okay. So, maybe for this specific case there is something, but when I change the code you will see it is a little bit more complicated. Okay. So, let us start with this. Okay. When do you say m is 0 0? You want so many things, right? You want 3 things to be true. What are the 3 things you want to be true? R1 plus R2 plus R3 plus R4, which is the correlation that you want, should be greater than R1 plus R3 minus R2 minus R4. Okay, the same guy should be greater than minus R1 minus R3 plus R2 plus R4, and then the last thing is minus R1 minus R2 minus R3 minus R4. Okay, so, like I was pointing out, you can maybe play around with these equations. Okay, so simplify some of them. Okay, all right. So, the condition you are getting here basically is this will become equivalent to R1 plus R3 being greater than 0, R2 plus R4 being greater than 0. The last one you do not have to check, because once these two are greater than 0, then last one will also be greater than 0. The last one is basically what? R1 plus R2 plus R3 plus R4 has to be greater than 0. So, it is a redundant condition. You do not have to check it. So, this is a simplification, but nevertheless you have these two things to check. Okay. If this is true, then you have okay possibility. Okay. So, this is something you can do, maybe you can even analyze this is not very hard, the simple enough code you can do it. Okay. So, you will have similar rules for m being 0 1, for m being 0 1 you will have similar rules, etc. Okay. 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 So, let us go to a slightly more complicated example. Our usual standard code, which was defined by this parity check matrix, I have been using it for syndrome decoding a lot. Okay. So, this is a 6,3 code, and if you want I can list out all the 8 code words. Okay, so, it is a bit of an effort to even write down the code words, but I will do it, so it will not take too much time. Hopefully, I am right. If I am making any mistake, let me know. Okay, so, those are the 8 code words. Well, the point I am trying to make is it is not so important to get all the code words exactly right, but when you will see what I am trying to say. Okay. So, it just becomes much more complicated. Okay. So, here the last 3 will take as the systematic part. Okay. So, that gives you the systematic part. Okay. So, suppose I say now what is the condition for m being 0 0 0. Okay. You will have 7 different conditions, okay, and it is not at all obvious what they are going to be. Okay, so this you are going to get strange conditions. Okay, so for instance, well, it is obvious what they are going to be, but it is not very clear what their interrelationship is. Okay, so for instance, one of the conditions will be, let me write down some of the conditions, it is not so hard. Okay, R1 plus R2 plus R4 is greater than 0, that will be the comparison with this guy. Comparison with this guy will be R1 plus R3 plus R5 is greater than 0. Okay. So, then the next one will be R2 plus R3 plus R6 is greater than 0. Do you see how I am getting it? It is just that correct? Okay, so you just you have to do a correlation with this and compare it with that correlation. Wherever there is 0, you are going to cancel it out. Wherever there is 1, you are going to move it to the left side, and then you can write R2 plus R3 plus R4 plus R5 is greater than 0. Likewise, okay, and there is no obvious way to combine any of it or make sense of any of it. Is there something which is redundant? It is a difficult question to answer. Okay, there might be, you never know, but it is hard to answer. Okay, so in general there may not. Okay, you may not be able to simplify anything. So, for instance, if you have to compute probability of error for the ML decoder, it is going to be a nightmare. Okay, why will it be a nightmare? What is it that you have to do? Okay. Okay, so what will happen is you are conditioning on the code word being all zeros. Okay. So, what you will end up getting is a large dimensional jointly Gaussian random variable for which you have to find some integration over the greater than 0 part. Okay. So, such integrations are impossible to get a nice closed form answer, you will not get a nice answer. Okay. You can approximate it, there are union bound techniques to approximate these things. Okay. So, that is what most people do. Okay. But the main lesson I want to convey is, suppose I ask you the question, same question I asked for the repetition code, which was, can you come up with the received vector which will give me different answers for the hard ML decoder and the soft ML decoder. It is a little bit harder already. Okay. It is not easy to get a good handle on what the ML decoder is doing, that is the big point I want to make. Okay. Particularly as your code becomes larger and larger, it is going to become messy. Okay. So, very hard to calculate. In general, the complexity will grow exponentially with k. Okay. It is going to be 2 power k. Okay. So, in general you need 2 power k correlations, and that is very complex to do. Okay. And you are not going to be able to finish it up in any finite time. Okay. Which was, I mean, this was, for instance, the hard syndrome decoder is quite simple in this particular case, at least. It is a very small decoder, you can very easily do it, and you can even analyze it, right. For the binary symmetric channel, you can very easily analyze, you will get a nice probability of error, everything can be done. Okay. But the soft, even this is a little bit difficult, you can do it, I am not saying it is impossible, theoretically it is a very simply defined problem, but in practice it is difficult to get a good answer. Okay. So, that is the ML decoder, and we will kind of leave the ML decoder here. Okay. So, we will come back to the ML decoder a little bit later in another context for some other code. Okay. So, it turns out for most linear block codes, people do not implement ML decoders. Okay. So, you can see why it is not very easy to get a handle on, people do not usually implement ML decoders, only approximations to it. Okay. Some approximations are easy, even there it is hard. Okay. What is in fact become much more popular today is the other kind of optimality that I was talking about, where you do not try and minimize the probability of block error, but you try and minimize the probability of bit error. Okay. So, it turns out for some reason that becomes like a better problem, because you can iterate on it. Okay. In the ML decoder, you get the answer in one shot or you do not, right. So, you did the entire code word in one shot and you do not. Okay. But it turns out when you do this bitwise optimal decoders, you can iterate on it, you can first get a slightly better estimate for each bit, and then a slightly better one, and then a slightly better one. Okay. That turns out to be incredibly useful in practice, because I mean you can stop whenever you want. That is something which is nice. I mean, it is just slightly better, eventually you stop. But in ML, such ideas have not really taken shape. Is there a way to slowly get something, and then make it slightly better, definitely moving towards the best possible? That people have to the best of my knowledge not succeeded really in finding efficient implementation, but for the bitwise optimal things they have succeeded, and so because of that bitwise things are much more popular today. Okay. So let us see how they work. So in the short time that we have I will be only able to define it, then I will define, we will see some examples and we will stop with them. Okay. So what we will see is bitwise optimal decode, soft decision decoder, soft decoders. Okay, you can ask me what about bitwise optimal hard decoders, they also exist. Okay, so they are also implemented, but soft decoders is what we will see. Okay, so we will see hard decoders a special case of this, so it is not much more difficult to handle. Okay, so we will do this first. Okay, so this optimality now, so remember my picture again, I have a code word C which goes through BPSK, became S, to which noise gets added, then you get R. I want to have a decoder which outputs, I will say some U. Okay, let us not say U, U is a bit misleading. I do not want to use C cap because it is not necessarily a code word. So let us just say, what else can we use here? Any ideas? We will do B. Okay, B is better, B for bit. Okay, so it will output a vector B, B1, B2, Bn. My goal here is that I want to minimize. Okay, so let us say C is C1, C2, Cn. I want to minimize probability that Bi is not equal to Ci, let us say for each I. Okay, so that is what I want to do. Okay, so there is some transmitted code word bit. I want to output a bit in the ith position, so that the probability that my output is not equal to the transmitted code word bit is minimal. That is what I want to minimize. Okay, so clearly there is no constraint that the entire vector should be a code word. Okay, so that is a big difference between bitwise optimal decoders and ML decoders. ML decoders will definitely output only a code word. Okay, by definition they will only look for other code words. Okay, bitwise optimal is different that way. Okay, fundamentally it is different. You only try to look at each bit. Okay, and then I output each bit which is the best for that. Okay, together there is no constraint that that should be a code word, that is not imposed, that is not necessary in the bitwise optimal decoder. Okay, in fact the best decoder which minimizes this probability of error will not necessarily output a code word all the time, which is very surprising. Okay, if you think about it, because the code word was definitely transmitted. Okay, but it's not constrained to do that. Okay, because particularly in the case that he was pointing out, for instance, one value becomes extremely noisy. Okay, in those cases it makes sense to output something which is not a code word. So that is why it handles those things in a different way. Okay, so how do we do this? Actually the way to do it is not very hard, I mean you know how to minimize any probability of error. You can go through the expression, you have to condition on the R and go through everything, you will get this condition. The condition you will get is what is known as the bitwise MAP condition. You basically say Bi is 0 if probability that Bi is 0 given R is greater than probability that Bi is 1 given R. Okay, and you say Bi is 1 otherwise. It is very simple. I mean you can use the similar arguments to before to show that the decision you have to make is like this. Okay, so given an R you have to compute these two probabilities which are known as the which you can say are bitwise MAP probabilities. What is MAP by the way? Maximum a posteriori. So these are basically a posteriori probabilities for each bit. Okay, you compute the a posteriori probability for Bi. and see if bi equal to 0 is greater than probability that bi is 1, okay. And if that is true, then you simply decide 0 or 1, okay. So now you know that probability that bi equal to 1 will be what? 1 minus probability that bi is 0 given r. So you can in fact only compute the left hand side and figure out if this will be greater, okay. So how do I do that? So let me see that. So all I have to do is probability that bi equals 0 given r is greater than, so bi is 0 if is greater than 1 minus, am I getting that right, probability that bi is 0 given r, okay. So you bring it to this side, you get probability that bi is 0 given r is greater than half. It is greater than half, clearly that is going to be greater than the other probability. So this is another equivalent condition, okay. Okay. Another very popular equivalent condition uses what is known as the log likelihood ratios, okay. So what you do is bi is 0, so you go back and see this, probability of bi is 0 given r greater than probability of bi is 1 given r, you divide both sides by the right hand side, okay. So you will get here probability that bi is 0 given r divided by probability that bi is 1 given r is greater than 1, okay. So this guy it's okay, so let me simplify this guy a little bit and I will call it something, okay. So now this guy on the left hand side we can write as, using Bayes rule, you can write it as f of r given bi is 0 times probability that bi is 0, of course divided by f of r, but anyway that will cancel with the denominator, so I do not have to worry about it, f of r given bi is 1 times probability that bi is 1. Remember what are these guys? These are a priori probabilities. If you assume your message is equally likely and if you assume your code is reasonable, what I mean by code is reasonable is the code will not be such that some bit is 0 all the time, okay. So you do not want to send a code where one bit is 0 all the time, you might as well not send it, okay. So if you do that, then it turns out for binary linear codes both of these will be equal and they will be equal to 0.5, okay. You can show that, it is not too difficult to show. So these two will cancel, okay. So this probably is one of your tutorial questions, you can go back and check that, there is maybe a proof for that also. So these two will cancel and you will be left with this, okay. So this ratio actually becomes the same as the ratio of the likelihood of r given bi is 0 and the likelihood of r given bi is 1. So this guy is called the likelihood ratio. We can call it the vector likelihood ratio just to say that you are taking the likelihood ratio for the entire vector r, okay. So remember that there is a cancellation that I am assuming here, but like I said for linear block codes it is true, but in some cases it will not be true, then you can't do the cancellation, you have to worry about what that means, okay. So but usually for BPSK AWGN you can cancel, it's no problem, okay. So this is the likelihood ratio and we will stop here, there is only about 30 seconds left, I do not want to introduce the next thing. So we will stop here and pick up from here in the next class.